Welcome. In this video, we are going to implement a great Instant NGP paper. Our implementation will rely solely on PyTorch, on Python, so there will be no dependence that needs compilation, no C++ backend, no CUDA backend. Well, PyTorch might include some, of course, but I mean, we will only depend on PyTorch as a backend. So basically, these are the results we'll get by the end of this video. So these are novel views generated from the test set. From the LEGO dataset. Let's dive in. That will be again just PyTorch implementation. I will put the link of this implementation in the description. If you find that good helpful, please leave it a star. That will plus 3. It helps to get discovered by other people, and it can help other people. And if you find this video helpful, please leave a thumbs up. It helps YouTube to understand that it's great content. So yeah, let's dive into the implementation. Again, these are the only package we're going to use. So PyTorch, NumPy, TQDM, on Pile, just to save the produced images. Let's dive directly into the NGP implementation. So we can start by creating the constructor. So we'll take as input T. So T is the number of entries in the hash table for each resolution. And L is the a list containing all the resolutions. So we are basically operating at different scales. So these are the list of resolutions. This is, for example, what you see in, I don't recall what is the number of the figure. For example, yeah, this figure you see, for example, you work at one resolution in pink, on another one in blue. And basically we do that at 3 different resolution, some coarse resolution, some fine resolutions. On NL will compute the list of all resolution we use. There is F. This is the dimension of each entry of the in the hash table. Typically, there's 2 that is used in the paper. L is the it's for encoding the direction into a higher dimensional space before feeding them to the MLP that predicts the color. Very standard in NeRF. In the NGP paper, I think they use spherical harmonics instead. But here, to make the implementation easier to understand and shorter, we are using positional encoding. And also AABB scale. So basically, NGP represents a bounded volume. Of course, you can combine it with other approach to make it work on unbounded scene. But here we are working with bounded scene. On AABB scale is the scale of the scene. So let's say that the scale is 3. That means that you are going your scene is centered on 0, and that you go from x equal minus 1.5 to x equal 1.5, and same for y and z. So yeah, AABB will determine the scale of the scene. Then we can directly move on to implementing the lookup table. So for each resolution in NL, we create a hash table, a grid of size t. By 2. Okay, this a mistake from my side here. To be fully generic, it should not be 2, but it should be f. But I've been so basically I've used 2 here. I've recorded 2, but it should be f instead. Sorry. Okay, so now we can move on to implementing the 3 prime numbers that are defined in the paper that are used for hashing the position x, y, z, and to map it into some index in those tables. We will do that in a moment, and then we can move on to implementing the density MLP. So the MLP that will predict the hidden units on the log density from the output from the current values from those tables, and then the color MLP. So the density MLP is a 1-layer MLP with a ReLU expression function and with 64 hidden units, while the color MLP is 2 hidden layers of 64 units, and is also using the ReLU. Of course, we're using the sigmoid at the end of the color MLP because it predicts a color between 0 and 1. The color MLP is taking 16 hidden units from the previous layer, from the density MLP, plus 27 units, which are basically the 3D direction encoded into a higher dimensional space. So yeah, let's implement the positional encoding. If you've looked at my previous videos on NeRF, you've seen that multiple times. So basically that's the standard positional encoding from the initial NeRF paper. Nothing crazy. Now we can move on to implementing the forward pass. So we can scale x by the scale of the scene, so that x, after scaling it by the scale of the scene, x will be between minus 0.5 and 5, assuming that x is within the bounds of the scene. So let's say that you say ABB scale is 3. That means that all the values in between minus 1.5 and 1.5 will be between minus 0.5 and 0.5. And therefore we create a mask to make sure that we only query the table on the neural networks for those values that are within the box. For all the values that are outside of the box, we will set the color and the density to 0 by default. And then what we do x plus equal 0.5, because we want x to be in between 0 and 1. Yeah, that yields better results. So yeah, this is what I was telling you for the color on the log sigma. By default, we set the color to 0. On the log sigma, we set it to minus 100,000, for example, so that when we take the exponential of that value, due to basically it will be rounded and it will be 0 for all the values that stays at that value. So basically we will only update the color on the log sigma for values that are within the bounding box, but all the value outside will remain at 0 on minus 100,000. So that means that when we compute sigma, it will be 0, which is what we want. Yeah, so we can prepare some variable, the features. So basically these are the features we'll extract from the, so for each resolution we'll extract features, and we will store all of them in that variable, and then that can be used to query the MLP. Okay, so we can iterate for the number of resolution. So we will first iterate row with coarse resolution, and then we'll little by little go to finer resolutions. So let's first start by computing the vertices. So basically for each value of x, and again we take the mask of x because we only want to compute x that are within the volume within the bounding box. So first we compute the floor on the ceiling of each x value. So basically that means that for given x here, we compute the for given resolution, for example the pink one, we compute the vertices. Here there are 4 because we're in 2D. If we're in 3D there are 8 vertices. So this is what we are doing in this code. Here I will use later nn.functional.gridSample from PyTorch to do a linear interpolation within that grid. So I need to be careful in the convention on how I define this grid, and yeah, I need to make sure that I'm using the same convention as this function is using, and that's why, for example, you can see that the indices are not monotonically increasing. I've made sure to use the right conventions. So once I compute the vertices from x and from the ceiling and the floor values of it, I can do the hashing. So this is the formula I use in the paper. So basically I'm converting the x, y, z coordinates into an index using the prime numbers and some bitwise operations. And then once I have this index, I can query the lookup table for the given resolution on that and the given index. And then I can reshape my volume, so I need to do some transposition and then some reshaping to get the shape needed by grid sample. And then so basically x is my initial position. I need to make sure that, for example, grid sample wants x to be between minus 0.5 and 0.5, so that's why I'm doing some computation there. But basically I'm creating a volume, or in that case a grid, with my vertices and with the features from each vertices, and then I'm using a grid sample to do a true linear interpolation, or in that case that will be linear interpolation, so that features closer to the point x have more weight than the others. We could have implemented that directly, in the same way we've implemented the querying of the tables directly. For example, we could also have used torch.embedding directly to query the tables, but I prefer to do it manually to get a better understanding. If we want to go deeper, we could also implement the linear interpolation, but here we are using a grid sample. So once we've queried the features for all resolution, we can feed them to to the density MLP to get the hidden units, so the 16 values. We can also prepare some conditioning. So we know that the color MLP will be conditioned on XCI. In that case, the only context we have is the embedded direction. For other papers, for example, NeRF in the wild, we will also have other extra input. For example, the latent space associated to each image. But okay, let's not talk about that for now. So basically, we are creating we create the embedding of the direction. We create the hidden features, and then we extract log sigma, which is which we define. This again a choice on a convention. We say the first value predicted by the density MLP will be the log sigma value, and then the color will be predicted by the color MLP using both the output from the density MLP and the conditioning. And then we can return the color and the density, and therefore we need to take the exponential of the log sigma to get the density. So yeah, because the density MLP is unconstrained, the value can go between -infinity and infinity, and that's why we model the log sigma, and then we take the exponential of it. That's a common practice, and again that's why we set -100,000 there, so that for those values that will be outside of the range of the volume, they will be to -100,000, and then when you take the exponential there will be 0. Okay, so let's move on. Now we can compute everything related to volumetric rendering. So for example, the compute acclimated transmittance. If you are following my videos, you've seen that a lot. That's coming from my course on NeRF. So if you're interested to learn more about NeRF in more generally, or to learn about volumetric rendering or about rendering in general, you might be interested in my course. People usually like it, and there are a lot of great reviews. Yeah, I will put the link in the description if you're interested. Now we can move on to the rendering function that will use the computer acclimated transmittance function we've just implemented. So it's take as input the NeRF model that will predict the color and the density for a given 3D point. We're taking rays as input that are parameterized by the origin and direction. We take the near and far plane and the number of bins, so number of points we are going to sample along each ray. In the NeRF paper, they do not use that approach. They are using ray marching on an occupancy grid. These are two components that have been omitted from this implementation for simplicity. You've seen that that gives good results. Maybe that could speed up the inference time and also the training. But yeah, here again we are focusing on simplicity. So we're just doing a volumetric rendering. So basically we sample T between the near and the far plane. Then we compute we add a bit of noise, so to make sure not to always sample the same points along the rays, which will lead to some overfitting. We add a bit of noise to the sample points to add some to add some randomness in the training, and then we compute the distance between each 3D point. This is delta, and that will be helpful to compute the volumetric rendering integral. So once we have T, we can compute the 3D location of each point. So by using the ray equation, so basically using the origin and the direction of each ray, we can compute this 3D location. Because we have for each ray, we sample multiple points along the ray. Excuse me. Then we need to reshape the direction so that we have excuse me again, we can associate one direction for each point along a ray, and then we can feed we can create the NeRF model with X, so the 3D location and the associated direction, and then we get a color on density for each point. Then from that we can compute the alpha value. So it's just a straight implementation from a direct implementation from the equations from the initial NeRF paper, and that also explained in depth in my course if you want more detail on that. And then we can compute the acclimated transmittance from the function we've defined. Again, that's a direct implementation of the equation from the initial NeRF paper. And then we can compute the final color by taking a weighted sum of the colors using the weights computed. And finally, this is only needed for a synthetic scene with a white background by using regularization. I've explained in some videos what's the point of that, so maybe I will not spend a lot of time on that. But yeah, basically it's just a regularization for specific case when we have white backgrounds. Now we can move on to the training function. As I like to say, basically it's just supervised learning because we have a rendering function. So basically for a given array we can predict what is the color associated by the model to that array, and then with the ground truth color, and therefore we can just take the L2 loss or any loss between those two values and get the final and then do a gradient step. So we can iterate over each batch in our data loader. Our batch are 9D, in which we have the origin, direction, and control pixel values. So given the array parameterized by the origin and direction, we can query the value of the predicted value of that array using the rendering function, and then take the loss between the control value and the predicted value. And then we can do one gradient step to update the NeRF model parameters. And then finally we can implement a testing function, and then we can put all our pieces together. So the testing function takes the near and far plane as input, similar to the training function. It also takes a dataset as input, the test dataset, the image index from the test dataset, basically the image we want to generate, a chunk size, because usually if you try to generate all your image at once, you will get out of memory errors on GPU. Then the number of bins, number of points you want to sample along each ray, and the size of the image. In this implementation we are going to use 800 by 800, but yeah, that's generally you could use any values you want. So basically first we query the array parameters from the dataset given the image index. Then we'll iterate over, so we'll create chunk of rays. So we will iterate over the number of chunks. We get chunks of ray origin and direction, and then we can render the values of those rays and add them in a list. And then we can turn this list into an image by first turning that into a tensor, and then reshaping it into the shape of an image, h by w by 3 channel, and then we can convert that into a pile image and save it in the hard drive. And finally, we can put everything together, so we can load the training and testing dataset that I've already pre-processed. I think it was my latest or two videos, I think it was my latest video. I made a video about how to generate those PKL files. So if you want to understand more like or like camera models work in NeRF, but also more generally like in rendering. So you might be interested in that video. But yeah, let's move on. So we load the datasets, then we generate the hyperparameters of the NGP model. So L, F, T, the shape of the tables again, Nmin and Nmax, the minimum and maximum resolutions. And then from once we have defined those two values, there is some formula. Basically we are just directly implementing the formulas from the paper that define the number of resolutions from Nmin and Nmax, on L the number of resolutions. So in that case we are going to use 16 different resolutions. So from very coarse values, so 16 to 2048. Then you can create the model by using the hyperparameters just defined, and then we can create the optimizer. So for the optimizer, they use different hyperparameters for each component. So basically the main difference, they use the same learning rate, the same beta, and the same epsilon values for each parameters. But for the lookup table, they do not use weight decay. But for the MLPs, both the density and the color models, they use a weight decay of 1e of 10 to the minus 6 to avoid overfitting or to avoid divergence when they train for longer. So once we've defined the model optimizer, we can create a data loader from the training dataset and then we can call the training function using all our predefined variable. And then once training is done, we can call the testing for each image from the test image. So there are 200 of them, and once you generate all those images, you can make a GIF. Yeah, that's really pleasant to see. And if you run this code, you should get results similar to the one I've presented at the beginning of this video. So I really hope this video is helpful to you to understand better Instant NGP. Again, not all components are implemented, but I think that's a nice way to get started and to understand what's going on in more details. So I really hope again that this video will be helpful to you. If it is, please leave a thumbs up, start this repository if you use the code from it, and yeah, subscribe for more content related to NeRF. Thank you.